Hello all, welcome to the next session class on digital system design. So till now we completed the module 2. So now we are going to learn the module 3. Okay. So till now what we have understood the circuits, digital circuits, those are all the combinational circuits. So you can recall that one in a digital electronic circuits we have two types of logical circuits. So one is called as a combinational logic circuit, another is called as a sequential logic circuit. So in the first module and the second module we discussed about the combinational circuits. So in the first session we understand the minimization techniques, and in the second modules we understood the different combinational circuits like encoders, decoders, adders, multiplexers, all those things we have understood. Okay. So now we will move to the module 3. So the module 3 is flip-flops and its applications. So here we are going to learn about some basic base table element and the different latches and the flip-flops and the master slave flip-flops, and there are different flip-flops actually, SR flip-flop, JK flip-flop, D and the T flip-flops are there, that we are going to be learned. Okay. And then we are going to learn the characteristics equations for the flip-flops. Okay. And then we are going to learn about the registers and the counters, applications of flip-flops, that is registers, okay, shift registers and the counters. So all those things we are going to learn in this module 3. So flip-flops and its applications. Okay. So till now what we have covered in the module 1 and module 2 are the combinational circuits. So this is the combinational circuit, where what is the combinational circuit? The present output of this circuit or a network is depends only on the present input. As when you give the input, according to that one the output will be changes actually, right? So even if you consider the adders or a multiplexers or any encoders also, as when you give the input, output will be correspondingly change that one. So if you want to add, if you give a 0 0, we are going to get a sum 0 and the carry 0. Okay, that what's the combinational circuit. Okay, but what is a sequential circuit then? So sequential circuit, again it is an logical circuit where the output of the circuit, it not only depends on the present input but also depends on the past output. Okay. So when you need depends on the past output means we need to save the previous output, right? So whatever the previous output will be there, that need to be stored. So that means we can say the sequential circuits will have a memory, but combination circuits does not have a memory actually. So this is an block diagram, we can represent a sequential circuit. So that means a combination, the sequential circuit will consisting a combination circuit also. Okay, but it is the output of that circuit which depends on even the past output. So that means they will going to have a feedback. Okay, so they will have a memory and they will have a feedback. Okay, a circuit which is having a feedback and memory, that is what a sequential circuit. So here you can see, so combination logic circuit with a feedback or a memory device will be there. Okay, the past output will be feedback to the as an input with the current input. According to these two inputs, the present outputs will be dependent. Okay, that is what the sequential circuit. Okay, that why here. So that we need to store the previous data. So that's why we need a memory. Okay, so whatever the data will be stored in the memory, that will be represented as a state actually. Okay, that is internal state or a state of the circuit or a state of the network. So that's why we can say inputs at any time to a sequential circuit along with the present internal state determines the output of the network. Present input what we are going to give, okay, and the internal state, present internal state corresponding to the whatever the data we have preserved in the memory, that data with the present input. So that whatever the data we have preserved, okay, and the present input, so that will going to be give the present output, okay, of the network. That is called as an actually sequential circuit. Okay. So here there are two types of sequential circuits are there. So the two types are, one is called as a synchronous sequential circuit, okay, another is called as an asynchronous sequential circuit. So synchronous sequential circuit means the output behavior, the output of the sequential circuit or a behavior of the sequential circuit is not going to change immediately when the changes in the input, but even it will going to wait for some particular time or a particular signal. So that is called as an actually synchronous, where that will going to have a clock actually. Okay, so we can say synchronous sequential network is the one in which the behavior is determined by the values of the signals at only discrete instant of time. At the particular instant of time, the output will going to be changes. So usually these networks will going to have the master clock. So that will going to have a clock will be there. When the input is given and the clock is given, then only the output will going to be changed. Okay, so that circuits are called as a synchronous sequential circuits or a network. Okay, so what about asynchronous? So asynchronous circuits, in this case the behavior of the network is immediately affected by the input signal changes. As the input signal changes, the output will going to be changes. Okay, but in a sequential, even the input changes, output won't be changes. Output will going to wait for the clock. Okay, so a clock with the input changes, that will going to give the output changes in the synchronous sequential circuit. But if you take an asynchronous sequential circuit, as the input changes, output will going to be change. Okay, so these are definitions of an synchronous and asynchronous sequential circuits. Okay, how the circuits will be there and the functions of the circuits, all those things we are going to learn in this module. Okay. So these sequential circuits have a memory, right? So already said. Okay, so the basic building block of any memory, that is called as a flip-flop. Okay, so the basic logic element that provides a memory in any sequential circuit is called as a flip-flop. Okay, so what is a flip-flop then? So flip-flop is a basic memory unit. Okay, so we are going to store in a 1-bit data. So that flip-flop we are going to have can store in 1-bit data. A flip-flop has a 2 stable conditions will be there. Each of these stable conditions is associated a state or a equivalently the storage of the binary symbols. The flip-flops will having a 2 states will be there. The corresponding to the binary 1 and the binary 0. So it can store a binary 1 value or which can store a binary 0 value. Okay, that's why we said a 2 states, 2 stable conditions will be there. Okay, so that what flip-flop is a memory unit. Okay, of any sequential circuit. Why we need a memory in a sequential circuit? Because the sequential circuits will going to change the output as per the present input and as well as the past output. To save the past output or to preserve the past output, we need a memory. Okay, these memory devices are built by the flip-flops. Okay, so that having a 2 states, that is state logic 1 and the state logic 0. So that can store a logic 1 or logic 0. So now we will move to the understanding about the flip-flop. Okay, so what is the structure of that one? We will going to understand. Okay, to understand that one flip-flops, okay, we need to understand a bistable element. Okay, so what is this basic bistable element? So basic bistable element, it is an main center of a flip-flop, or we can say this is a basic building block of any flip-flop. So because this circuit will going to be hold the any stable conditions. Okay. So that what is central of all the flip-flop circuit is the basic bistable element. Okay. So how this basic bistable will be there? So this is the basic bistable element diagram. So here we have a 2 NOT gates will be there. So we will represent as a NOT gate 1 and this is a NOT gate 2. Okay. NOT gate 1 is having input X and the output will be the Q. Okay. And the NOT gate 2. So second down one. Okay. So this is having input Y and the output will be the Q bar. Okay, so there we have a 2 outputs Q and the Q bar, a NOT gate which are in the cross coupled. Cross coupled means, okay, so that means the output of the first NOT gate is connected as an input to the second. So similarly, so the second NOT gate output is connected as an input to the first NOT gate. So that's why we call it as a cross coupled. Okay, this is a bistable element. Okay. So it has 2 outputs, that's Q and the Q bar. Okay, this corresponds to Q bar. Okay, so it has 2 cross coupled NOT gates. So I already said what is a cross coupled. The output of the first NOT gate is serving as an input to the second NOT gate. Okay, and the output of the second NOT gate serving as an input for the first NOT gate. Okay, that is called as a cross coupled. Okay, so this will be the connection. Okay. So and it is having a 2 stable states will be there. Okay. So what are the 2 stable states? Let's understand that one. So I will go to write that one here. So we have a 1 NOT gate and another NOT gate. These are the cross coupled. Okay. The input for the first NOT gate is X and the output is Q, and the input for the second NOT gate is Y and the output will be the Q bar. Okay. Assuming that one, now we are going to give a certain X equals to 0. When X equals to 0. Okay, when x equals to 0, so what will be the q? Q is what the not operation of the x. So that means this is will be equals to the x bar. So that means if you give x equals to 0 and the q will be the 1. Alright? Okay. And since it's a cross coupled, so this 1 whatever you're going to give in here, so that will be act as input actually. So that means we can say x bar will be equals to the y, and since this will be the 1. Okay, and this is 1 means, so again what will be the q bar, and q bar will be the y complement, and this will be equals to again a 0. Okay, and this 0 is again feeding to the first NOR gate because cross coupled. So that means always when the x equals to 0, if that is the case, always the q will be 1 and the q bar will be the 0. Okay, so that is what. So thus the circuit will be stable with the q bar will be equals to 0 and the q equals to 1. Always this circuit will be having a stably will going to give the logic 1 output. Okay, and here logic 0. Actually in this q and q bar we will consider as a normal output will be the q, and the complement of that output will be the q bar actually. So we have a two outputs q and q bar, okay, where q is called as an actually normal output, where q bar is the complement of that. Okay, so similarly if you give a x equals to 1, so what will going to happen? So here we are going to give a x equals to 1, so that means x bar that will going to give a 0, and this 0 will going to feed into the y. So here we are getting a 0, so that means q bar will going to be the logic 1. So that means when x equals to 1, we always will going to have a stable value of a q equals to 0 and the q bar will be equals to the logic 1. Okay, so that's what. Similarly, when x equals to 1, so we are going to get a q bar will be always 1 and the q will be always 0. So thus the circuit will be stable with the q bar with a 1 and the q with a 0. So that's why we said so it has a two stable states. So we are going to have a logic 1 and the logic 0. Okay, and this circuit always will going to give a logic 0 when x is equals to 1 when the device is turned on. So this bistable element is turned on, or give a power means always will going to give a 0. Okay, so that's why we are going to say a stable output will be generated. So when the output line the q will be 1, so then the element will going to be store the logic 1. Similarly, when the q output is equal to 0, then we are going to be storing the logic 0. So this is a bistable element which is an basic building of any flip-flop. We can store a logic 1 or a logic 0. How will going to be stored? That is what. When you turned off this one, so you are going to give a logic 1 or a logic 0. It's giving a logic 1 means it's storing the 1, logic 1, and that is why binary value 1 is stored. If the output is 0 means, so it is storing the logic 0, or it is having a binary value 0. Okay, so that is what the bistable element, basic bistable element, which will going to store the logic 1 or a logic 0. So binary symbols that is stored in the basic bistable is referred as an content or a state of the element. Okay, so that will whatever they are going to store, that is considered state 0 or a state 1. The state of the basic bistable element is given by the signal value at the q output. That means we are going to consider the output with only the q, where q bar will be considered as a complement of that. Okay, but output is what? The q. Okay, hence the q output terminally is called as a normal output, as already said. So that's why we call as a q terminal output is a normal output, and the q bar is considered as a complement of that, complement output. Okay, so when the q equals to 0 means it is storing the logic 0 or a binary 0. Is the q equals to 1 means it is stored the logic 1. So when the device is storing a 1, so this is said to be a state 1 state. It's called as an 1 state. Okay, or we call as even the set. Okay, that means so when this having a logic 1 is there, and that means so it will going to call as the bistable element is set. So that means it is having an 1 state or a logic 1 state. Okay. Similarly, if the q is equals to 0 means, okay, I can say q equals to 0, so then we call as an reset. So that means when it's storing the logic 0, or we can say 0 state. Okay. So these are the basic bistable element will having a two stable conditions. Okay, there is no other states will be there. Okay, but only when the logical symbols is not exactly not able to determine, it is a logic 0 or logic 1. So example, if it should be logic 0, but is not able to identify it as a logic 0 or logic 1 due to the some noise in the circuit. Okay, then that is called as a metastable state, where that is not able to identify that which is a logic 0 or a logic 1. Okay, that is called as an metastable state. Okay, so that what here. This other state may be occur. So the occurs when the two output signals are halfway between the logic 0 and the logic 1. That what. So it is not even the logic 0, but even in the not in the logic 1. Okay, so due to the some noise actually that the signal will be in the halfway between the 0 and the logic 1. So this is the logic 0 and this is the logic 1. Okay, logic 0 volts assuming, and the logic 1 corresponds to the some 5 volts, some threshold will be there. Okay, so in between that one, so this is not able to identify it is a logic 1 or a logic 0, and that state is called as an actually metastable state. Okay, so we need to overcome is any changes should be happen. Okay, that what any small changes causes the element to enter one of its two stable states. So if it is a metastable state, so any one of the changes is there. So if it is in the halfway between the logic 0 and logic 1, if it move to the logic 0, then it will be the any one of the stable outputs. That is 0, that means reset. If it is to the 1 means it will be a set. Okay, so the amount of time, so how much time it will be there in the metastable condition, that is unknown actually. Okay, that depends on the circuit. Okay, so metastable state must be avoided. Okay, and we need to avoid the metastable state. Okay, if the circuit is moved to the metastable state means we don't know what is the response of that circuit. It won't give a logic 1 also, it won't give a logic 0. So that is what a forbidden. Okay, so we are not able to understand the response of the circuit. So that will be a problem actually. Okay, that's why we need to avoid the metastable state in any flip-flop. Okay, or we can say a bistable element. Okay, and this bistable element is not having any inputs actually. Okay, so x equals to 1 you are going to give a logic 0, or if x equals to 0 you are going to give a logic 1. Okay, there is no other inputs will be there. So that what here. So bistable element has a no inputs. Okay, and keep in mind when the power is applied, it becomes stable in one of the two stable states and remains in this state until the power is off. So that means when this device is turned on, so always, so we are going to give a logic 0 if x equals to 1, and always we are going to give a logic 1 if x equals to 0. Okay, so according to that we will always give a one state will be there, and when this is turned on, so always it will be in the any one of the stable states will be there. But practically circuits which is having only a one state, it is no use actually. We need to change the states according to our requirement. Okay, that means we need to give the inputs. Okay, so the bistable elements with inputs if we give, and that will call as a flip-flop. So that's why we said the basic bistable element is the center of the flip-flop. Okay, so that what a flip-flop is a bistable device with inputs. Okay, we are going to give the inputs according to the inputs of the state. So the whatever that may be 1 or is 0, that can be changed. Okay, so a flip-flop is a bistable device with inputs that remains in a given state as long as the power is applied and until the input signals are applied to cause the output change. Okay, so until there is no changes in the inputs or the changes in the power, so we are going to give the same output. Okay, logic 1 it will going to give the logic 1 only or a set mode. When the inputs are changes, okay, then the output may be changed. So that is what is an flip-flop. So there are two ways we can give the inputs to the flip-flop to make the changes in the output. Okay, so we can give two types of the inputs. So one is called as a synchronous input, another is called as an asynchronous input. Okay, the similar to the synchronous sequential circuit and the synchronous sequential circuit. The synchronous are a direct input, okay, where the signal changes produces an immediate changes in the state of the flip-flop. Okay, as the inputs are changes, okay, output will be immediately changes. That is called as an actually a asynchronous input. Okay, when you give the input, output will be suddenly changes for a flip-flop. But even the input is given, the output does not changes immediately, but it will going to wait for another specific time, or that is what the specific input, that is called as a clock. Okay, then that is called as a synchronous flip-flops inputs. Okay, see, synchronous input, okay, a signal which does not immediately affect the state of the flip-flop, okay, affect it only when some control signal is occurs. So that is usually a clock. So next we'll move to the latches. Latches are also a storage devices, and these latches are a class of flip-flops. Okay, and the outputs of these latches will be immediately changes as the input changes, and these latches will going to be interrogated the input lines continuously. Okay, that means we can say input lines are continuously being interrogated. So in the latches, so there are several latches are available. Okay, so based on the input lines and the enable lines. Okay, so let's see the one by one. Okay, the first latch is what the SR latch. Okay, so SR latch is corresponds to the set and reset latch, and here S and R corresponds to the set and reset. Okay, the SR latch is an cross coupled of two NOR gates. So you can see the diagram here actually. So this is one NOR gate and this is another NOR gate. Okay, so this is a cross coupled of a NOR gate. Okay, so we will given the inputs R and S. So if you see the bistable element, we don't have any inputs. See, right? Okay, but we need to change the states of the bistable element. We need to force the input. Okay, so that's why we'll comes to the concept of latches and the flip-flops. Okay, so that's our latches. So here we have the two inputs. The two inputs corresponding to the S and R, and this refers to the set and the reset. Okay, so this can be right in the by using the NOR or even in this way, or then will be the NOT. Okay, so this is the logic circuit diagram of the SR latch, and this diagram will going to give the logic symbol of the SR latch. Okay, so logic symbol which consists in the two inputs and the two outputs. The two outputs are the Q and the Q bar, and the two inputs are the S and the R. Okay, you can represent it like this or even like this. Here will be Q bar represented, here will be Q with its complement. So bubble is given, that is indicates what the Q bar, complement of the Q. Okay, and this is the function table of the SR latch. Okay, where in the function table we indicated the Q plus and the Q bar plus. Okay, and the Q is Q bar. So let's understand what all these terminologies. Okay, so Q plus indicates what the output of Q responds to the inputs. Okay, when they give the inputs to the S and R. Okay, so whatever the inputs will going to give to the latch. Okay, and when you give the input, whatever the corresponding response will going to come, so that will be represented as a Q plus. Okay, which indicates as the next state actually. So then what about the Q? And Q is the present state of the latch. So that means, so when you are giving the input, whatever the Q will be available, that Q is called as a present state. So you can see here, Q is the state of the device at the time of the input signals are applied. Okay, when you are giving the inputs, okay, whatever the state of the latch will be there, that state is what the present state, that will be indicated with the Q, and when the inputs are applied, whatever the response you are going to get, that will be represented as a Q plus, and that is the next state of the latch. Okay, so these two are need to be understand. Okay, so Q plus, so in this column we are going to get the next state of the Q, and this Q bar plus indicates the next state of the Q bar. Okay, and this is the Q and this is the Q bar plus. Okay, so let's understand this function table. So when the inputs of the SR latch are 0, 0, so when you give the input to the S and R are 0, 0, then the output of the next state of the latch, or even the response for the inputs 0, 0, that will be the previous state only, or we can the whatever the present state will be there, that will going to be continue. Okay, so that means what Q and the Q bar. Let's analyze that one by applying to this circuit. Okay, so this is R and this is S, Q and the Q bar, right? Okay, now when S equals to 0 and R equals to 0, let's understand. Okay. Now we are giving a R equals to 0 and S equals to 0. Okay. Now to compute the output of the NOR gate, okay, we need even the previous output of the Q bar. Okay, that means whatever the when you are going the input, whatever the state will be there, present state, that we needed actually. Okay, so for that one only, I will assume Q equals to 1 and Q bar equals to 0. Okay, so now that means Q bar was 0 and the Q is 1. So now, so what is the output of the first NOR gate? So it's 0 and Q bar is 0 and 0 NOR with 0, and we are going to get a logic 1 here, right? Okay, so let's have the NOR 2 table also. So that will going to help for us. A plus B whole bar 0 0 0 1 1 0 1 1 0 plus 0 0 1 0 0 0, right? So this is the NOR 2 table. Okay, so when this is given a 0 plus 0, we will going to get a 1. Now this 1 will going to apply here, and the present input is S0 and 0 1, that is equals to 1, 1 plus 0 we will going to get a 0. Okay, that means what is the present output? The present output is, that is indicated as a Q plus. So Q plus equals to 1 and the Q bar plus, that is equals to 0. So this was the previous state. Okay, that means, so when you are giving the input, what were the state of the output Q and Q bar, that is what the 1 and 0. Now after the applying the input, so the next state of the Q, that is what the Q plus and the Q bar plus will go to get the as same as the previous one. See, so that is what the Q plus will be equals to Q and the Q bar plus even will be equals to the Q bar. So that's why we will go to write as a, so when you giving the input S and R are 0 0, that will going to retain the previous state. Whatever the state will be there, that will be continued. Okay, so that is what the output when the input for the S and R latch will be the 0 0. Okay, and this state will called as an similar to a bistable state. Okay, that means what we have discussed in the previous, the same state. Okay, because when you give that will going to maintain the constant output, or a stable output will be maintained when the device is turned on. If it is a 1 logic 1, it always will going to give a logic 1. So that is what here. So if it is a 1, so if you give a S equals to R equals to 0, it will going to maintain the same 1 actually. So that's why we will call this as an similar to a bistable state. So that what. So when S equals and R equals to 0, logic diagram simplifies us of a basic bistable element. So similar like a bistable element only. So always we are going to continue the whatever the state will be there, that will going to be continue. Okay. So here I have taken S equals to 1 and Q bar equals to 0. So what about if I assuming the Q equals to 0 and Q bar equals to 1? So again also that will be Q plus and the Q bar plus will follows the previous only. Let's consider that one also. Assume Q equals to 0 and Q bar equals to 1. Okay, so this is the when S bar R equals to 0, and this is the first case and this is the second case within the when S equals to 0 and R equals to 0. Okay, so now Q equals to 0, let's analyze here, and we are giving R equals to 0 and we are giving the S equals to 0. Okay, so now what is the previous Q bar? That is equals to 1. So we are giving here 1. So 0 plus 1. Okay, 0 plus 1 we are going to get the output will be 0, and this 0 will going to come here actually. Okay, 0 0 and that will going to give the 1. So that means when we are assuming the Q equals to 0 and Q bar equals to 1, so the next output, the Q plus will be 0 and the Q bar plus will be equals to 1. Okay, so that indicates what? So when the S and R are 0 0, so we are going to retain the whatever the previous state is there. So that means we are going to get the Q and the Q bar. So Q plus will be as similar as a Q. So by analyzing this one, we can say Q plus will be Q and Q bar plus will be equals to Q bar. Okay, So this is what the response of an SR latch when the inputs of a S and R are the 0, 0. Okay, so hope you understood. So let's analyze what is the response of an SR latch when the inputs are 0 and 1. So now when the S equals to 0 and R equals to 1. Okay, so I will erase this. S equals to 0 and R equals to 1. Okay, let's analyze the function of the SR latch when the S equals to 0 and R equals to 1. Okay, so again we need the previous output, or whatever when giving the input, whatever the present state will be there of the Q and Q bar that we needed. So let's assume Q equals to 1 and the Q bar equals to 0. Okay, so that means we are going to give a Q bar 0 here. Let's analyze this one. So 1 plus 0 we are going to get the output will be 0. Okay, and this will 0 will going to give here actually. So 0 plus 0, so output will be the 1. Okay, so that means Q plus will be equals to the 0 and the Q bar plus will be equals to the 1. So when we are giving the input, Q equals to 1 and the Q bar equals to 0. Okay, similarly considering the Q equals to 0 and the Q bar equals to 1. Okay, assuming when we are applying the input, whatever the present state will be there, if assuming that as an Q equals to 0 and the Q bar equals to 1, so this here we are giving the 1, so 1 plus 1 we are going to get a 0. Okay, this 0 will be fed to the second NOR gate and this will going to give a logic 1. So that indicates what? So the next state of the SR latch when they given the inputs are S0 and R equals to 1, that will going to give a Q plus equals to 0 and the Q bar plus equals to 1. Okay, so what does this indicates what? When the input is equals to when the inputs of S equals to 0 and R equals to 1, always the output will be a 0. Always the Q plus will going to be given a 0. Okay, so whatever it may be the previous. So the previous is what? 1 0. The next state will be the 0 1, and even if the previous output is 0 1, the next state will be always a 0 1 only. So this indicates Q plus always will be 0 and the Q bar plus will be always equals to 1, and this state is called as a reset state. So when you are giving the reset input to the 1 and the set input to the 0, then the flip flop will going to be a reset. So that means we are going to give a 0. Okay, so that means we are going to be storing the logic 0. Earlier, whatever it may be the data binary value of the flip flop, that will go to force to the store to the 0 or force to the reset when we are giving the input S equals to 0 and R equals to the 1. So this is how we are going to force the state of the latch by giving the input. Okay, that is what the difference in the bistable element and the latch or a flip flop. Okay, so that what here in the bistable element we are not able to force the output or force the states of the element, bistable element. Okay, but here by applying the input we can change that state of that latch. Okay, so you can see here actually that what. So when S equals to 0 and R equals to 1, always Q plus will going to give a 0 and the Q bar plus will going to give a logic 1. Okay, so this is what is the SR latch response when the input is equals to S0 and the R1, and this state is called as a reset. So that's what when R equals to 1 and S equals to 0, this latch is going to be a reset. Okay, that means it will going to be 0. Okay, so what going to happen when the S equals to 1 and the R equals to 1? Let's analyze. Okay, so when the S equals to 1 and R equals to 0, what will be the output? The next state of the latch. Let's analyze that one. But again, to calculate the next state, again we need to assume the what is the present state or the what is the output when you are giving the input. Okay, so here R equals to 0 and S equals to 1. So let's assume q equals to 1 and the q bar equals to 0. Okay, whatever the present q and the q bar is 1 0, and then okay, let's analyze the circuit. Okay, so when r equals to 0 and the present state is q bar equals to 0, then the output will going to be the 1. Okay, and this 1 will going to be fed to the next NOR gate, and 1 plus 1, that will going to give the 0. So that indicates the next state, the q plus will become a 1 and the q bar plus will be 0. Okay, similarly, let's analyze the circuit assuming the present state q equals to 0 and q bar equals to 1. Assume q equals to 0 and q bar equals to 1. So here s equals to 1 and whatever the q input will going to be, the assuming is the previous will be the 0. So 0 plus 1, so that will going to give a 0, and this 0 is given to here, actually 0 plus 0 will going to get the logic 1 here. So that indicates what? So q plus will be equals to 1 and the q bar plus that will be equals to the 0. Okay, by analyzing this we can say q plus will be always 1 and the q bar plus will be always 0. Okay, so that indicates, so when the s equals to 1 and r equals to 0, okay, so output or the next states will be always a 1 0. Okay, and this state is called as a set state. Okay, so that means we are giving the logic 1 to the set and we are giving a logic 0 to the reset pin. Okay, so this will going to set the output, that will going to set the output of the latches to the logic 1. Okay, so this is what is the response of an latch when the s equals to 1 and r equals to 0. So next let's analyze the SR latch, where will be the output. So when the input s and r are equals to 1 1. Okay, let's analyze this one. When s equals to 1 and the r equals to 1, so that means we are giving the both the inputs are 1 1. Okay, let's assume the present state q equals to 1 and the q bar equals to 0. Okay, so that means we are giving a 0 here. So 0 plus 1 output will be 0. So and this 0 is going to be fed to the next NOR gate. So that will going to give the again a 0. See here both the outputs q plus and the q plus bar both are will going to be a 0. And we have observed that when there is no complementary actually. So we know that actually q plus and the q bar plus must be complement. So here we are getting the both outputs are 0. This state is called as an actually a forbidden state. Okay, and we need to avoid this state in an SR latch actually. Okay, so when the S1 and R1 both are equals to 1 1, so see that is what. So output both the NOR gates becomes a 0 and is now not complementary. Okay, and we need to avoid this forbidden state actually. Okay, the state is called as an S equals to R regard as an forbidden state, and we need to avoid this one. Okay, so in this case when the S and R both are 1 1, if the inputs of the any one of the inputs S equals to 1 R equals to 1 will be returned to the 0. Okay, and then we can calculate the final output actually. Okay, so if one of the input returns to 0 before the other, okay, the last input to stay at the 1 determines the final state. Okay, whatever the last state will be there, that will be the final state. Okay, assuming that one, when this is the condition, if S equals to suddenly becomes 0 and this q bar will become a 1, so that will going to give the output will be a 0 1. Okay, but if the S and R both are becomes a 0 simultaneously, see, if the both the input returns to 0 simultaneously, the device may enters its metastable state. So what I have said already, we discussed the metastable state where the output will be not able to defined. So this will be in the between the 0 and the logic between the logic 0 and the logic 1. Okay, where the output is not able to define. So that is going to the final state is unpredictable. Okay, and we need to avoid this state when you are using the SR latch. Okay, so hope you understood the functionality of the SR latch. Okay, so SR latch is what the set and reset latch. Okay, the function table of the SR latch will be like this. When the 0 0, that follows the previous, okay, S equals to 0 or equals to 1, output will be always a reset, that means logic 0, and when the S equals to 1 and R equals to 0, output will be set, okay, that is Q will be 1, and when the S equals to 1 and R equals to 1, the both outputs will be 0, that is what the forbidden state. Okay, and we need to avoid that state when you are operating the SR latch. Okay, so this is with respect to the SR latch. Okay, now let us see the application of an SR latch. Okay, let us move to the application of an SR latch, a switch debouncer. Okay, so considering a mechanical switch such as a toggle switch or a push button switch. Okay, for example, we can say our keyboard switch, okay, a computer keyboard switch. Okay, that's similar like a push button switch. Okay, so when you are using a push button switch, okay, so due to the spring actions in the push button switch, okay, that will going to leads to a switch bounce. Okay, switch bounce, that means what? So that will be the on and off will going to be takes place when you are moving the push from the one point to the another point. Okay, so we can see here actually, so this is the switch. Okay, so this is the point A and the point B. Okay, so when you have need to connect from the point A to the point B or a point B to the point A, so that will be the bouncing action will going to be takes place. Okay, so let's analyze that one actually. Okay, so this is the voltage V. Okay, and this is the contact point B. Okay, and this is the point A. Okay, assuming that one, now the contact is towards to the B. Okay, so voltage corresponding to the point B is represented in a waveform here actually. Okay, similarly the voltage corresponding to the point A will be represented here actually. Okay, so now when the contact is at B, so we are going to have the positive voltage. Okay, so that's why B equals to VB is equals to 1 and the VA equals to 0. Okay, now we press the switch. Okay, that means what? The contact will be moved from the B to the A. Okay, so when this contact is disconnect from the point B, okay, automatically the voltage of B will become a 0, and this will going to go into contact with the A. Okay, so the waveform at A will be the positive voltage. Okay, but due to this switch spring operation, okay, make and break operations will going to take place. That means connect and disconnect, that will going to be happen due to the springness of the switch or a toggle switch or a push button switch. That will going to happen when the contact is away from the A, the voltage will become a 0, and again when it is connected it will become a positive voltage. Again when it comes to the away from the A, so again will go become a 0. After the complete of the springness it will going to be connected, then it will going to give a positive voltage. Okay, keep in mind that one, on that time it won't come to the contact B, so that's why the entire contact B will become a 0. Okay, so due to this action, so this is what is called as a switch bounce. Okay, so this is due to the switch bounce operations, we cannot able to predict the output, it is 1 or 0. So that will be the problem, and the same problem will going to be happens again when we are moving the contact from the switch point A to the point B. So again due to the spring actions, the bouncing actions, okay, again that will going to be repeat here also. So when you are moving from the contact from A to B or from the B to A, so that bouncing actions will going to be takes place. Now we need to avoid this one. Okay, we can eliminate this effect by using the switch debouncer. So switch debouncer is what, whatever the switch will be there, that will be connected to an SR latch, and the pull down resistance are connected to the inputs of the S and R. Okay, so now what will be the operation going to take place? Let's analyze. Okay, again here, so assuming that initially it will be in the point B. Okay, so this is what the point. Okay, switch A will be, B will be plus volts and A equals to 0. Okay, so when the contact is moved to the from A to B, again the bouncing action will going to take place, but since we have connected the pull down resistors, so when the A and B, when the contact is between the A and B, that means it's not connected to the A or not connected to the B, due to the pull down resistance, the SR inputs will be in the 0 state. So we know that in SR latch, when the inputs S and R are 0, so that will go to give the previous output, right? So you can see here actually. So when the S and 0 and R 0, that will going to maintain the whatever the previous output, that will be the next output. Okay, so this will going to be helpful here. Okay, and that waveform will be represented here actually. So this is the waveform corresponding to the switch bouncing action, and this is the output corresponding to the switch debouncer. Okay, when the contact is moved from the B to A, so when is A is touched to that one, so this will going to give the SR inputs. So where the B is connected to the R, so that is 0, and A is connected to the S, and that will become a 1. Okay, that will go into the 1 0 output. In 1 0 input, when the 1 0 input to the SR latch, and the Q will become a 1. So always this is going to maintain this state. Even there is an switch bounce. So assuming that one, the contact will be moved away from the A, okay, and due to some bouncing action, but it does not change as here Q, because so when the contact is away from the A, okay, where the inputs of the S and R will be always a 0 0 due to the pull down resistors. Okay, due to that, when these inputs are 0 0, that will going to maintain the previous output. So what is the previous output is Q, and Q will be maintained. So like that, we will going to avoid the switch bouncing action. Okay, without a flip flop, so that will be bouncing going to takes place. Okay, so output will be having a 1 0 1 0, that will be bouncing will go to takes place, but here there is no such cases. Okay, so always you are going to maintain a 1. So when this is contact into the B, okay, output will be a 0. When we move from the B to A, automatically output will always will be the logic 1. And when we move from the A to B, okay, again output will become a 0. Again, when you move from the contact, when you move from the A to B, even there is a bouncing action also, the Q will be becomes a 0. Okay, in this time A equals to 0, that means S equals to 0, B equals to 1, that means R equals to 1. Okay, so that means Q will becomes a 0. So this will going to be a maintained. So even, so due to the bouncing action, if the contact is away from the A also, due to the pull down resistance, S and R will be a 0 point. Okay, so when S and R 0, that will going to maintain the previous state. So that means there is no bouncing action. Okay, so this is what the switch debouncer. Okay, this is an application of an SR latch. So hope you understood this one. Okay, as already said, we have a different latches. Okay, so we have an S bar, R bar latch. Okay, D latch, gated D latch, like that. Okay, that we're going to learn in the next class. Thank you.